Hello, calculus students and general seekers of truth. In this lesson, we will discuss and learn about antiderivatives. We've seen this slightly before in a previous lesson on particle motion, and the purpose of this lesson is to formalize the understanding of what an antiderivative is and how to find them in a slightly more systematic way. So let us begin with a formal definition, and formal definition usually means there's some symbolic logic to this. So this basically means that you have two functions, big F and little f. And big F is the antiderivative, in other words, the reverse derivative of little f, if the derivative of big F is equal to little f. So maybe I could give you a very, very quick example. So let's say here that you have some function, big F of x equals 3. Okay, so it's a constant function, 3x, I'm sorry. Then the derivative of f prime, or the derivative of big F, is equal to 3. So that means, so that would in this case be little f. So if you take the derivative of something and you get a result, then the first thing is the antiderivative of the second one. In other words, if we had a function like f of x equals 3, and we were to find its antiderivative, would be to go in reverse, then we could say that its antiderivative is equal to 3x. Now, this is a formal definition, and it's not so important that you memorize a formal definition as much as it is that you can understand and apply it. Okay? So, I'm going to walk through the rest of this lesson here is based on giving you some explanations of some very specific cases. So let's say that you have a function whose derivative is a constant. So let's say you took the derivative of something and you got that the derivative of it was a constant. Then that means its antiderivative would be equal to kx, okay, plus c. Now, this c here represents some other constant. C is called is some other constant. So we could verify this quite simply. I mean, the beauty of finding antiderivative is that it's very simple to check or verify. All you have to do is take the derivative again. So let's say this was the original function. Well, its derivative, right, would just be equal to k, because the derivative of a constant times x is the constant, and this constant of integration here, this constant of antiderivative here goes away altogether. Because what's unique about an antiderivative is that there are infinitely many antiderivatives. So there are infinitely many antiderivatives because you could just attach a little constant to the end and come up with a brand new antiderivative, because the derivative of any constant is 0. So let me give you maybe a more concrete example. So let's say that f prime of x was equal to 17. Well, what could f of x be equal to? Well, we kind of reverse the process of differentiation, and we can say that f of x could be 17x. But f of x could also be 17x plus 80. And that's a perfectly legitimate solution. And f of x could also be equal to 17x minus 125. That's also a perfectly good solution. And so you see this constant here at the end, you can add anything you want to here. So we add a generic letter. We call that the constant in abstraction. that just represents all the different possible constant that we could attach to the end here. So let's keep on going, and let's work on the power rule for antiderivatives. So let's say you had a derivative, which is ax to the nth. So this is kind of like an exponential, not an exponential, a polynomial, although n could also be a fraction. So its antiderivative would be a, we're going to leave a alone, that's constant in front, times n, and we're going backwards here. So normally you would subtract 1 from n, and now all you have to do is add 1 to it. But remember that when you take the derivative of f, you're going to have to multiply by n plus 1, and in order to get rid of it, you need to be able to divide by n plus 1. And once again, the proof of these antiderivatives are, well, pretty darn simple. I should say plus another constant back here. So the proof is really simple. This is my claim, and I'm going to prove it simply by taking the derivative. What would f prime be equal to? Well, remember that a and n are all constants here, so we would have a over n plus 1. So if I were to take the derivative of this, I would pull down the n plus 1 to the front. And then I have x to the n plus 1 minus 1, which is just x to the n. And then this constant would go away altogether. So simplifying, this goes away and this goes away. So what we're left with is f prime of x is equal to ax to the n. So once again, to check if the antiderivative is correct, it's relatively simple. All you have to do is take its derivative and see if you get back to what you were given to begin with. Now, I should point out here in this video that this doesn't work if n is equal to -1. N could be equal to anything, but not -1. And we'll see in the next video why that is the case.